Welcome to the mutually exclusive and non-mutually exclusive probability video. We have previously gone over both independent and dependent events. So looking at situations where two things happen and we're looking at both of them occurring. So event A and event B happening. Now we're going to be looking at scenarios where we're going to have the keyword or. Somewhere in the question, we'll be talking about event A or event B happening. And then there's two different ways to kind of branch out from there. So one example is mutually exclusive events, where event A and event B could never happen at the same time. For example, could you have a queen and a 3 in the same card? Absolutely not. There's no way that one playing card could be a queen and a 3. But could you have a red card that is also a queen? Yes, there's two ways to do that. There's a queen of hearts, there's a queen of diamonds. There's two ways that a card could be a queen and be a red card. So when there's no overlap or no intersection, we call it mutually exclusive. It's like a club where, you've got definite separation between the groups. In the case where it's possible that something could be in both groups, that there is some intersection or there is an overlap, then that's what they call non-mutually exclusive events. So let's first look at the mutually exclusive event, where we're going to take the two probabilities and add them together, and then we'll come back to the non-mutually exclusive events after. So in our first example, we have two classes that are occurring at the same time, and it's impossible to schedule students in the two classes because they occur at the same time. So we're going to imagine sort of the student body. And if you will, I'm just going to make a big square to show the whole universe, the whole, this is the set of all the students that are at our school. And if we make one group, we're going to make one group of applied math students. And I'm going to put like 12% of the student body inside that set. So this is just a visual. This is sort of what's going on in my mind. And 4% are taking psychology, but there's no possible way that there's an overlap between these two groups because they occur at the same time. So when it's asking what's the probability a student takes applied or psychology, with the word or, we're going to be adding them together. So we're going to take the probability of being an applied, so 12%. You could use a decimal or you could use the percent. And you could add it to the probability of being in psychology. So 16% chance that one of the students is going to be in either applied or psychology. So next question, what is the probability a student at the school does not take applied? So does not, whenever we're seeing that word not, we're thinking about the complement. So the complement being one or one whole student body. So let's say 100%. And I'm just going to use the actual percent. So might as well take 100% and subtract off the probability of a student actually being in applied. So the probability of event A actually happening. And if we subtract that, then we'll get 88% not in applied. And what is the probability that a student does not take psychology or applied? So, we could look at this and write it out like this, with the line on top. So not being in applied or psychology would be the 100% minus the actual chance of being in applied or psychology. So So this one's a little bit easy because there is no intersection. There's no way to sort of be in both. We could actually include this 84% just down here. When we write it outside of the circles, it's showing that it's still within the set of students, and this is showing the 84% that are not part of those groups. So here's a sample that's similar to what we were just looking at. We've got a set of students. We have a group of applied students. We have a group of essential math students. And lo and behold, there's some students that are actually taking both. So we're just going to interpret this diagram here. So what's the probability that a student is in an applied class? Well, first of all, we should probably find our total number of students. So let's add together all of our numbers. So there's 140 that don't take those math classes, 40 that are only in applied, 8 that are in both, and 212 that are in essentials. And I'm hoping that this adds up to 400. I should double check. Yeah, 400. So out of the 400 students, how many are taking applied? I know we want to jump right in and say 40, but realistically, we're looking at this whole group being applied students. All of those students are taking applied. So it's 40 plus 8, so 48 students are taking applied. How many students are taking essentials? Again, it'll be out of 400. So it's the 212 that are only taking essentials plus the 8 to make 220 that are taking essentials. How many are taking both applied and essentials? So both is another way to describe that. That's the intersection. That's the overlap. Only 8 out of the 400 students are taking both applied and essentials. So now the question is how many students are taking applied or essentials? We have to be really, really careful here because our instinct is to add, and you would be right, but we can't necessarily add that 48 plus the 220. So if we take 48 and we add the 220, we've actually added the intersection twice. We've duplicated it. So we're going to take the probability of somebody being in applied math and the probability of somebody being in essential math. And we're going to subtract off one instance where they're in both. So this looks like 48 out of 400 plus 220 out of 400. And then we're going to minus off the 8. And we're just going to subtract it off once because the 8 is in here and the 8 is in here. So let's get that. So that gives us 260 out of 400 are in either applied or essentials. And then another sample question, is a nice one. Another complement kind of question. How many students are not in applied? When we talk about students not being applied, we're talking about the 140 that are not in either one of our math classes and also these 212 that are only in essentials. So from applied, we want to look at all of those. So we would, have 140 plus the 212. So let's take one more look at another question kind of like this that's showing us our non-mutually exclusive formula. So here now we can kind of create the whole piece. We've got 400 students total. We know 48 are going to take applied math. We know 35 are going to take art. And we know 6 take both. So the challenge here and the stumble is that people will just write 400 and 48 and 6 and 35, and they'll just fill in the Venn diagram using the values that are in the question. But the only thing that we know for sure that's really true about this is the 6. We know that it is true that there are 6 that take both. If we backtrack and we look at the 48 altogether, then we know that 42 must be only taking applied. 42 and 6 make the 48. If 6 are taking both, that must leave us with 29 that are only taking art. And we'll just don't have a lot of room here. Let's do 400 minus the 42 minus 6 minus 29. So, how many students take applied or art? Well, we can have 48 out of 400 for taking applied. We can have 35 out of 400 for taking art. And we're going to subtract off the chance that they're taking both. So that's 6 out of 400. So that leaves us with 77 out of 400 are taking applied or art. What's the probability that a student does not take art? So in order to not take art, we would take the whole. So 100% of the students are 400 students and subtract off the 35 that are taking art. So 365 not taking art. Here, I'll just change my color up so this doesn't, it's running right off the page. How many do not take applied or art? Well, there we go. We have that right here. So we've got our total of 400 and then subtracting off all of the applied or the art. So there's 323 out of the 400 that are not taking applied or art. So sometimes creating the diagram can also be helpful. But we can certainly just use our mutually exclusive or non-mutually exclusive formulas there.